So if you look at the top there where it says 5.3 continued, on Friday we did the first day and we were evaluating a definite integral. Now what we're dealing with is the idea, it's called the average value of a definite integral. So we're still dealing with these definite integrals, still now talking about an average value of those, and it's very similar to what you're thinking when we did average in the past. So the word mean basically is your average. Typically what that means is you're going to add up all of your numbers in your data set and then divide them by the number of items in that set. Okay, old idea. This is actually somewhat similar. What we're going to be finding is the mean value theorem of basically a definite integral slash the mean value theorem of a function. So what this really gets at is how can we find the average value of any function that we want over a certain interval. So if you look at what I have set up here, it's really pretty simple. If you look here, here's what we did on Friday, what I have highlighted here, that's our definite integral. We can't really add up an infinite number of points. So if I wanted you, so if we kind of look at number 2 real quick. Oh, why is that not working? If you look at number 2 here, that's why. If I wanted you to find the average value of the square root curve from 0 to 16, it's impossible to add every single numerical point functional value along this curve and then divide it by that number, because in reality, it's kind of an infinite number. But that's what we're going to ultimately be doing when we do this, is finding what's the average y value of the square root of curve from 0 to 16. And the way we do that is by taking the value of our integral like we did on Friday. And then what we're really doing is now we're going to be dividing by the interval that we covered. So typically it would just kind of look like this. But what we're just doing to simplify that a little bit, we're pulling that fraction out. And instead of dividing by b minus a, we're going to kind of ignore it, pull it out as 1 over b minus a, but it's effectively the same thing as just dividing it by the interval that we have got covered. All right. I actually want to do number 2 first, because I think it makes the most sense in terms of explaining it. It's easiest to see. Because if I were to ask you what the average value of this function would be, the square root of 16 is 4. So would we all agree the average value better fit somewhere between a 0 and a 4? All right, it would have to be. So our answer to this question, if we understand what this is really asking us, is what's the average value of this function? Sometimes people ask, why don't we just do 0 to 16? Well, if I did that, the functional value at 16 would have been a 4, plus the value at 0 would have been a 0, divide that by 2, and we would say that 2 is our average value. But that's not the average value of the function. That's only the average value at 2 points. What the average value theorem does, it actually does take into account every single y value in between 0 and 16, averages them all together, and actually gives us the real average of all of those at once. Okay, which is kind of weird to think of that is possible. So as we do this one, what we're going to be doing, we're going to set up the definite integral of our function. So whatever function I want the average value of, that's the one that we're going to set up within our integral. We're going to go over the interval of 0 to 16. So that looks like what we did Friday. All we're doing now today to find an average is we're going to divide it by the interval that we just covered, which in this case will be a 16. So the 1/16, we're going to kind of ignore that for a while. We're not going to really have to deal with that until the very end. Root x is an x. Think of this as a power of a half. So we're going to add 1 to that power. So that gives us 3/2. You're going to divide by 3/2, which is the same as multiplying by 2/3. And then we're going to evaluate that over the interval of 0 to 16. I'm going to go ahead, while we're doing it, I'm going to combine these, simplify that down a little bit. That should be, what, 2 over 48? What is that, 1 over 24? I'm going to go ahead and plug in my 16 and my 0. I'm also going to rewrite this as a square root of 16 cubed minus, this would be a square root of 0 cubed. And then these are almost all, not almost, they are always non-calculator. So we should be able to handle this. We'll see who's clever here. You should be, I would expect you to be able to do the square root of 16 cubed without a calculator. We were in class, and we had a quiz, and I gave you this problem. That is something that we should be able to do without our calculator. So see if you can be clever because you probably don't really want to do 16 times 16 times 16, because that's going to be an extremely large number. And if you know your multiples and square roots of that, then I'd be very, very impressed. Let's see if we could simplify that. How could we simplify that? And it's actually a really, really nice number. And then keeping in mind, we better get an answer between 0 and 4. The average value better fit between 0 and 4, because that's the biggest y value and the smallest y value of this curve. Okay, anybody clever? I want to share some clever ways of evaluating this thing. Yeah, brave souls. Ryan, he
64.
How'd you get that, Ryan?
So I did the 16 3 over 2, and I split up to 16 to the 1/2 power times 16 to the 2 over 2, and then 16 to the 1/2 is square root of 16, which is 4 times 16, which would be 64.
Wow, you did that with fraction powers, right? I'm impressed. Okay, so Ryan actually did this with fraction powers. I don't know if you could hear him at home, but he took this and he did 16 to the 1/2, and then 16 to, did you say that 2 over 2? Because if we multiply those together, that's going to give us our 16 to the 3/2. Now, I wouldn't have done it that way, but it effectively is the same exact thing. So what I had is 16 cubed. So the way I would have simplified this, but it's basically the same, he did it with fractional powers, is couldn't we have done this as a square root of 16 squared multiplied by then that third 16, which is the square root of 16. So either way now, so what he does nicely, I kind of like this, that's just a 16, right? I get my 16 right here. Doesn't the square root and the square cancel each other out? And I'm just going to get a 16. So I get 1 over 24. So these guys here become our 16. Here's where I kind of like mine a little better, just because the square root of 16 we know is a 4. But what Ryan gave us is the half. And if you understand that's a radical, that is square root, that also is going to give you your 4. So we said that should equal 64. And then we're dividing that by 24, so that's good. Reduce that, and then this should be a reasonable answer. This is saying between 0 and 16, 8/3, so about 2 2/3, that is the average y value that the square root of x takes within the interval of 0 to 16. So that's what we're solving when we do. So just kind of keep in mind what we're looking for. These are going to be pretty, I actually gave you some harder integrals to evaluate because we've already done definite integrals. But when we start cranking these out, because we did these on Friday, that's what we're looking for. It's easy to kind of lose sight of that. That's why I like doing number 2 first. Okay, so now when we go to number 1, much easier, and we don't have to spend as much time. You're going to do 1 over 4 minus 0. We're going to integrate the sine of x from 0 to 4. Drop the 1/4. The antiderivative of sine is a negative cosine, so I'm going to put the negative out with the 1/4. Leave the negative 1/4 with the cosine if you like, but like I've mentioned a number of times at this point, I like leaving it out. And then I'm just plugging into a cosine. So I would do the cosine of our upper limit minus the cosine of our lower limit. Not much you can do with this. You wouldn't have a calculator in your hand. There's no way for you to evaluate cosine of 4, so that's just our answer. You could distribute if you like, but that's good enough. All right. And to start with 1, it's hard, like, who even knows what this number is, really, right? Like, who the heck knows? So it's hard to talk about how that's the average value of our sine curve, but that is what it is. If I were just kind of sketch out the sine curve and go from 0 to 4, that's all those y values averaged together would take on this overall value. Okay. All right, number 3, same thing. We're going to go from 1 over e cubed minus e, and then our lower limit's e, upper limit's e cubed, and then our integral is 2 over x. Don't be one of the people who think we can combine these. We cannot combine those, correct? It's basically the same as x cubed minus x. You cannot combine x cubed minus an x. So we can't combine an x or an e cubed minus an e. So that's just going to stay the same. This should give us a 2, and then this is 1 over x. That's our natural log, absolute value from e to e cubed. So we get 1 over e cubed minus e. Plug in your upper limits, plug in your lower limit. Reviewed some of our natural log values the other day and how we can simplify all of those. So these should just cancel, giving us a 3. The natural log of e is what gives us a value of 1. Final answer then is 4 over e cubed minus e. Okay. Now, number 4, I usually, and I will, this is our longer class, see if you can go all the way through number 4. Like I said, we did a bunch of definite integrals Friday. So the mechanics of this we should have down pat. So I gave you a little harder ones now to deal with, just as a review of some older topics. See if you can go all the way through number 4 and give me a nice, if I were to give you a multiple choice answer, nice simplified answer to this. And see what you think you would get. Actually, stop. Don't go any further. Do me a favor, because I don't want people to get lucky and then not understand but still get the right answer. Change this to a natural log of 8. So this guy right, oops, I didn't want to do that. Change this to an 8. And then that way I'll make sure we get this correct. Understand why it is what it is. A little more than meets the eye with this. Then if I were to make a test, quiz, whatever, really I could go either way with this. See if you get one of these 2 answers. I could write the 12 over a natural log of 16. Or, make sure I do this right. Yeah, 6 over the natural log of 4 would be one of the 2 you would hopefully get. This is a good review of all of our natural log properties or exponential properties. How do they tie into each other? We haven't had to deal with a whole lot recently. Seeing a lot of strange looks on our faces, so we'll go ahead and get started here. See if we can get through it. It's up to you what you want to do with this. But we can simplify this right now. You don't necessarily need to simplify that right now. At some point, though, you're going to want to understand this. So what we want to remember is if I have two natural logs, which I do here, and we are subtracting those, I can combine that into one natural log if I divide their insides. So that coefficient can become a 1 over ln of 4. All right, and that's why I wanted you to change this. So I don't want people thinking this is a natural log of 6. Like it can't do 8 minus a 2 and get a 6. And if this was a 4 still, I'm afraid people would have said 4 minus 2 is a 2 when you're really doing 4 divided by 2, which is a 2. So this becomes a natural log of 4. The antiderivative, hopefully that's not an issue. Then I'm going to take the 2 out because I like to do that. So I'm going to write this as 1 over 2 ln of 4. And then now all I'm really plugging into is this 2e to the x. That would be the only thing left over. So I would get e 2 to the ln of 8 minus e 2 to the ln of, or 2 ln of 2. So this is why I could go either route. You could simplify this to be a natural log of 16, correct? You can make that 2 the exponent of the 4. It's a natural log of 16. I'm going to leave that now just so we can see how we can get both of these answers. So I'm going to leave this right now as 2 ln of 4. The big thing I wanted to make sure we understood is we can't cancel these out right now, right? The e has to be raised directly to the natural log. So the little 2 in front is the problem. We don't want to cancel those out just yet until we've taken this 2 and made it the exponent of the 8. Then we can say these cancel. So what that first term actually now becomes is a 16. And then the same thing here. This 2 needs to become the power of 2. So that when these cancel, we get a minus a 4. So one of our answers, well, here's how we can get our 2 answers now. So you should get the 12 over 2 ln of 4. If we divide those right now, the 12 and the 2 would give you the 6, and then you get over the natural log of 4. Or you could do the 12 and then make this 2 the power of the 4 to get a natural log of 16. Okay. So good little review there of some old stuff that we haven't seen in a while. Nice little problem there. Looks simple enough when you look at it, but it's some tricks there. Yeah.
It's supposed to be an
8 squared.
8 times 2.
Oh yeah. Good call. Oh, maybe that's why I was getting all the strange looks. Yeah. And I'm convincing myself. You know what? Ryan was looking all weird. And that's usually when I'm in class and I can see all the weird looks. I know I did something silly. Yeah, good call, Aaron. Should be 64, right? So this would be, yeah, so let's change these answers. Is that why everybody's looking at me crazy, hopefully? Okay, good. That's worthy of a crazy look, I suppose. Yeah, so 64 over 2 ln of 4. Or 32 over ln of 4. All right, either one of those. Okay. All right, last one. Again, old idea. Another one. Yeah, who said that?
Wait, why is it 64 over natural log of 16?
Oh yeah, because now I'm flustered, Devanshi. This is my flustered. See, with my mask on, this is my flustered look. Same as my happy look, same as my serious look. They're all the same. Yeah, so let's fix this. Yeah, so we want 60 now. So we would get what, 30 over ln of 4, or we would call that 60 over ln of 16. Right. So let's just pretend that didn't happen there. Let's get rid of those guys. Okay. Now number 5. It'll set up pretty easily. It's just the very, very last part that you're going to have to recall something. We reached it a little bit on Friday with something, but this one's a little harder. So setting these up at this point, nobody has a problem with that. You'll have your 1/2. We better know this is inverse tangent at this point from a -1 to 1. And what I want to see is, can we evaluate those? Let's see what you get. Let's see what we got here. The first one should be nice. I would hope this guy isn't a problem. You're trying to figure out, so what we've always talked about is the first quadrant always works. So that's what you want to look at first. So if we can find a value in the first quadrant, that if I did my inverse tangent, which is the y coordinate divided by the x coordinate to get a 1, then we pick that, and there certainly is. So right here at pi over 4, or pi over 4 is when we get root 2 over 2, we're going to divide those, we're going to get a 1. So that should give us a pi over 4. Minus, then we get to the inverse tangent of a negative 1. And then now we've got to remember some of that older stuff, because there isn't a first quadrant angle where I can take a y divided by an x and get a negative 1. So the first thing you had to understand is what quadrants work for this, what was our domain. So the inverse, or the range, the inverse tangent's range is the first quadrant and the fourth quadrant. But you have to be careful of just considering them quadrants. Okay, we really want to kind of know the range interval, because what that then tells us is it has to be the pi over 4 angle in the fourth quadrant. And if you just think quadrants, first and fourth, you may be fooled to think that this is going to be 7 pi over 4 for our answer, because that certainly satisfies that fourth quadrant angle for the pi over 4. Our issue, though, is the interval for inverse tangents range is a negative pi over 2 to a positive pi over 2. So this 7 pi over 4 is if we go all the way around the circle in the normal counterclockwise direction, but 7 pi over 4 doesn't fit in that window. So what we have to do is take a shortcut and go backwards, clockwise, 45 degrees, and call this negative pi over 4. Then it fits in the window where it's supposed to fit. All right. So we have 2 pi over 4 here. So then our answer is pi over 4. All right. So I kind of use some of these as old review of some things we haven't had to deal with in a while, because the new idea is pretty simple. The average value of a function is now a definite integral divided by the interval that you're going to cover. Okay. All right. Then last thing here, and you want to see these because this is sort of what the AP question gets at next page. So it says, or for the homework, the table below gives selected values of your velocity in meters per second. So that's our bottom row. Particle traveling on a straight line. I want you to use 2 different methods: the average rate of change, old idea, and then the average value, which is our new idea, to find an average acceleration. So if you're given, let me make this a little smaller. So if we understand that position, velocity, acceleration, you're given a velocity. One of the ways that we could have done it before today, the way you probably would have done this, at least hopefully if we remember this, if I want to go from velocity to an acceleration, it's the idea of a derivative. So if this is our velocity and I want an acceleration, the average rate of change acts as the approximation tool for our derivative. So since I want you to go from 2 to 6, we would set up f of 6 minus f of 2 over 6 minus 2. And if you want to be very official about it, even more correct about it, you could actually say that this is v of 6 minus v of 2, because then that actually is showing it's my velocity with respect to time. We know that's going to be our acceleration. My velocity at 6 seconds is this 13 right here. My velocity at 2 seconds would be the 7. So what we would get is, and think about our units, the 13 and 7 had units of meters per second. The 6 and the 2 had a unit of seconds. So I get 6/4, which is 3/2 meters per second. So I've just approximated my acceleration, my rate of change of velocity over the interval of 2 to 6. Okay, that's the old way, still valid, no problem doing that. But what we now want to understand is, how can we use this new idea if I'm looking for an average value and I want an average acceleration? So when we say if I want the average value of a function, so we come up here, average value of a function, the function doesn't have to be f. Isn't a derivative still a function? Or isn't a second derivative still a function? Your velocity is a function. So when we say the average value, we want the average value of whatever I'm asking you to find the average value of. So when we come down here for letter B, I want you to find the average acceleration. So I can set up one of these average value problems that we just did. So 1 over 6 minus 2 from 2 to 6. And then I put in here whatever I'm trying to find the average value of. And in this case, I am trying to find an average acceleration. So I would put a of t. We don't actually have it defined with a function, but that's what I'm putting in there. That's what I want the average value of. If it said average velocity, you're going to put v in there. So now, do the same thing we did at the top. We don't have an actual acceleration function, but we do know if I do the antiderivative of a of t, that should bring me up to v of t. And then we evaluate that from 2 to 6. And then we would plug in our upper limit, subtract our lower limit. And aren't we at this step essentially doing the exact same thing that we did in the previous step? I'm going to take my velocity value at 6 seconds of 13, my velocity value at 2 seconds, which is 7. So this is my change in velocity, that's 6, but then I'm going to divide it by that 4, which is my change in time, and I would still get 3/2 meters per second squared. All right, so just a different way now that we could approach an average acceleration, average velocity, average whatever. All right. All right, next one. So it's using the chart above, find the value of this now. So here's our velocity table. I want you to integrate the velocity table from 0 to 8. We don't have a velocity function, so we've got to approximate it. I'm going to have you approximate it with 2 midpoint rectangles of equal base. So the first thing we have to do is figure out what are our bases, and that's what we called our change in x. I guess in this case, it'd be our change in time. If you put change in x, that's not a problem though. You can leave the x there. Our interval that we're covering is 8 minus 0, and I want 2 rectangles. So to keep these equal, we're going to move over 4 seconds each time. I again suggest you draw these in. So I'm going to go up from, starting at 0. I'm going to move over 4 seconds. So that will give me rectangle number 1 here. And then I've got to move over another 4 seconds. That should take me to 8. And then that should give me rectangle number 2. Make this a little smaller. You can see both. So then what we're going to set up, come on, you switch. The integral from 0 to 8, integrating my velocity. Again, we can't do this. You could try this. You could try to say, yeah, my antiderivative of velocity is my position. And then some situations we could do this. But do we have any position information given to us here? No. So we don't know our position at 8. We don't know our position at 0. So that wouldn't get us very far. Plus, I'm telling you to use rectangles. So for rectangle number 1, I want you to now think of this a little differently. Our old way of thinking about this is the area of rectangles, where this was our height and that's our base. So the base of all of these is 4. So if we do it the old way, we would say that our base is 4. We find that out right at the beginning. And then we would want the height, what did we say, midpoint, right? Yeah. So if I go to rectangle number 1, here is its midpoint. And the height at the midpoint would have been 7. So we plug in a 7. That's the old way of thinking it, still perfectly valid. Now think of it using a definite integral. Aren't I really taking my velocity value and multiplying it by my change in time? So what 7 stands for, isn't this my velocity value at the midpoint rectangle? And we're going to multiply that by my change in time. Isn't my change in time what I found right here of 4? And then remember what the integral means. It's a sum, right? So once we have our 2 different products of velocities and changes in time, you're going to add those up. So if we go to the rectangle number 2, let's use that idea. I want to take my velocity value and multiply it by my change in time. Well, my change in time is still 4. And the velocity value at the midpoint, here's the midpoint, 13 is my velocity value at the midpoint. We then add those. So what is that? 28 plus 52. Now I'm doubting myself. We all get 80? It does not sound familiar to me. I feel like that's wrong. All right, so we get 80, and then that is going to have a unit of, now understand our units, this was meters per second times seconds. The velocity value, meters per second times seconds. So each time this guy had a unit of meters per second, this guy had a unit of seconds. Multiplying those together should give us meters. And then I say, using correct units, explain this answer. So now, when we explain what we just found here, ooh, I ran out of space too. If I enter a couple different ways we could approach it. When I integrate velocity, doesn't that take us to our position? So what we've just calculated is the change in the position of, what was this, just a particle? Yeah, that's boring. Position of the particle. And when you explain these, which you'll have to do, and on the AP test, they will absolutely make you do this, you also then need to say from, when we're explaining a definite integral, from t equals 0 to t equals 8 seconds. So we want two different units in play here, right? The unit that we just found, which is meters, but then we also want to explain our limits from 0 to 8 and then attach the correct unit to our unit or to our limits as well. All right. It's sort of why I'm giving you that AP question tonight, because you're gonna have to do something pretty similar. I want to make sure we understand that and can do that. All right. Okay, real quick, I was afraid this is gonna happen. Go to the back page. There's one that you very much want to see for your test. So I want to make sure we do that. So pretty simple little setup. You're given a function, P is a constant, we don't know what it is. A and B, we're not going to do. C, you're going to want to make sure you can do this in 48 hours, something similar. There's one of these on the test review also. I did that one in the video. So if you watch the video, the same idea. If you read through letter C, it says find the value of P. So we're actually going to figure out what is this unknown constant in this problem. And the way we're going to do that is we're going to do that knowing that the average value of our function, so what we did on the front page, over the interval of a -1 to 2 is 1. So if you think old algebra 1 word problem, remember how the is was always your equal to? You were setting up an equation. So we're going to set this equation up. The right-hand side is equal to a 1. Pretty straightforward. Everything before that is the left-hand side. So it's the average value of our function over this interval. So we're going to have 1 over 2 minus the -1, integrating from a -1 to 2. And then our function is that x cubed minus 6x squared plus p. It's just a different way of testing you on your ability to evaluate a definite integral. Notice how this is now an equation here. So we're going to solve this equation by basically doing our definite integral. So we're going to take this here, the 1 over the 3, from a -1 to 2. It's up to you. You don't necessarily need to. I think it would be the prudent, easiest thing to do. But since this is now nothing more than an equation, we could multiply by 3 and get rid of that 3 on both sides. Since we're a little short on time, I'm going to cheat and just erase. So that's going to go away. And then this 1 over here is going to become a 3. Really, really common question for you to see an unknown within the integral or to make one of your limits unknown. All we have to do this is just do what we've been doing with definite integrals. The antiderivative of x cubed would be x to the 4th over 4 minus 6x cubed over 3, so 2x cubed. Careful with your p. The antiderivative of p, since p is a constant, like think about the antiderivative of 6. Wouldn't the antiderivative of 6 be 6x? So the derivative of any constant, which in this case is p, would just be px. And then you're going to evaluate that from -1 to 2. And then that would equal a 3. And then we know, plug in your upper limit first. So if I take my 2 to the 4th would be 16/4. So that's a 4. If I plug in my 2 here, I get 8 times 2, so 16. And if I let the x be a 2 here, I would get 2p. Close that. That's your upper limit plugged in. Subtract. Throw in your lower limit. A negative 1 to the 4th power would be a positive 1, so we get 1/4. A negative 1 cubed would be a negative 1 times a negative 2, so this should become a positive 2. And then minus, let this x be a negative 1, we get a negative p. And then all of that equals 3. Now, probably don't have time to go through all of this because we are less than a minute, but don't we now just have a regular old equation that we could go through and solve? It's messy, you got some fractions, there's a lot of stuff that needs to be cleaned up, but at this point now, you're just looking at a regular equation that you need to go through and solve. I believe this is going off of memory. I have not done this. I think it might be 23/4, but just solve that equation. That should give you your final answer. There's another one of those on the review. I go through it in detail with you on the video, but definitely know how to do something like that on Friday. There's going to be 2 of those like that on your tests. I'm sorry, on Wednesday. Okay? All right. We'll see you guys. Have a good day. All right. Bye, Aaron. CC. Bye, CC.